Welcome everybody who's just joining. We're going to wait a few minutes before we get started. Uh, Hi, welcome everybody. We're going to wait a few minutes before we get started. So hold tight and we'll start shortly. Hi, good morning everyone. Welcome. We're going to give it one more minute and then we'll jump in and get started. Hi, good morning, everyone. Welcome. We're going to wait 30 more seconds and then we'll kick it off. Thank you for your patience. All right. I think we have a lot of people joining. So thank you for taking some time out of your day to join us. And I'll hand it over to Vivian Clay to start the meeting. Take it away, Vivian.
All right, thanks. Yeah, welcome everyone. I'm Vivian Clay, Director of the Thousand Brains Project. And today we hope to give you a high-level overview of the Thousand Brains Project and the new type of AI that we're building. And so we set up a series of 9 short talks. So everyone from our team will present a different aspect of the project. Not all talks have the same length, so don't worry if by the halfway mark we're not through half of the talks. Overall, it will take about 2 hours, but in case you have to drop off at any point, we're also recording this meeting. If you have any questions, feel free to post them throughout in the Q&A section, and then we will answer them in the end. And you can also upvote other people's questions if you would find them interesting. So yeah, we hope that you'll walk away from today's talk series with interest and excitement about what we're doing. And there are many ways in which you can help us. You can contribute code, build applications, or tell others about the Thousand Brains project. We think that, yeah, what we're creating is really exciting and important, and we hope you'll feel the same way at the end of this. Just a brief intro of what the Thousand Brains project is, in case you haven't heard much about us yet. Thousand Brains project is a nonprofit company that was created at the beginning of this year. And we believe that the future of AI and robotics will be based on sensory motor learning. And so we're building a sensory motor AI platform. We call it Monty. So if you hear the term Monty throughout today's talks, that's what we call our AI platform. And this is a new type of machine intelligence based on the principles of the neocortex as laid out in the Thousand Brains theory. It's not deep learning, it's not LLMs. It's really a different type of AI that's specifically designed for sensory motor learning. It's super efficient, both in terms of energy use and data use, can do continual learning and a bunch of other exciting stuff that our brain can do. And you'll hear a lot about that later. And we also want to make it accessible to anyone. So it's everything is open source. We upload all our meetings on YouTube. Associated patents are under a non-assert pledge, and we're trying to build a really vibrant community around this project and really build this together with all of you if you're interested. And yeah, a lot of talks later will also touch about this part of the project. But to start, let me tell you the story of this special project and what we're doing and how we got to where we are today. And to tell this story, I'll use a fun visual analogy. So we often talk about how the brain uses reference frames to efficiently represent structured knowledge. And you can think of reference frames as coordinate systems or maps that represent how different things in the world are related to each other. And here I will use a map as my reference frame to lay out the structure of the project. And I hope it helps you follow along, or is at least an entertaining way to hear the story of the project. So without further ado, here's the Legend of Monty. On a foggy October morning, the crew at Numenta, which is where this project started, arrived at the shores of Monty Island. We didn't know much about this island, but the captain of the ship, Jeff Hawkins, had a clear vision. One, that we can reverse engineer the brain, and two, that machine intelligence based on the brain's principles will be the most important technology of the 21st century. And with that vision, we started out to explore this island. We also had a really useful compass. which is the thousand brains theory. And through almost 20 years of studying the brain, this theory was developed, and we used the principles as a guide. Scott will talk more about those principles later, but just at a very high level, to give you an idea of what those are. One is sensory motor learning. So everything is about learning through movement. Our eyes move about 3 times a second. Our whole bodies move. There's really no intelligence on this planet that doesn't move around. So everything about the system is about learning through interacting with the world. Second, having a general repeatable processing unit modeled after cortical columns in the neocortex. Third, local information and learning. So each of these general processing units only receives very local information about a small patch on the retina or a small patch of skin, and there's no big picture anywhere. And also learning isn't a kind of global process, but very local. And fourth, reference frames. So what I mentioned earlier, a way to represent how knowledge relates to each other. And so these principles have served us really well so far as we were exploring this island, and we've been using it as a good compass on any kind of decision point throughout. Based on those principles, we build a basic framework for a new AI system, and we call it Monty, after Vernon Mountcastle, neuroscientist that first proposed the idea of a general repeatable processing unit in the brain. Next, we set out to build the components of Monty. We set up a first settlement to construct learning modules, and we constructed them after what's known about cortical columns and their architecture and connectivity. Another settlement specialized in the construction of sensor modules. Sensor modules are basically the interface between Monty and the world. They take in raw sensory data from any kind of modality and translate it into a language that learning modules can understand. And we also had to define the connectivity between learning modules and sensor modules. And so we defined a set of traffic rules for messages sent between sensor modules and learning modules within the Monty framework. And we call that the cortical messaging protocol. We iterated on the learning module design several times until an individual learning module could achieve robust object and pose recognition. So we could learn an object taking one path along the object and then do inference on the object in a totally new orientation, taking a never-before-taken path on the object under noisy conditions, which is pretty cool. We call this the evidence learning module and still use it today. Over time, we improved sensor module capabilities and built a new settlement specialized in the design of intelligent policies. So thus far, Monty moved largely random, but by now we have several more sophisticated model-free and model-based policies that Monty can use to efficiently explore the world using either the sensory input or its learned models and hypotheses. A new monastery in the forest started investigating scaling the system to more learning modules. They implemented, tested the first versions of voting between learning modules to reach rapid consensus during inference. Settlement with craftsmen specializing on optimizing the implementation led to significant speedups of the system. Another scouting party ventured off to explore the possibility of stacking learning modules on top of each other to learn more complex compositional models through hierarchy. We also ventured out to the lake and tested the innovations so far in the real world. This was a week-long hackathon. We termed the project Monty Meets World, and it was really exciting to see Monty work outside of the simulator for the first time. We could put an object in front of an iPad camera and recognize it, and that felt really special at the time. After a lot of the initial infrastructure was put down, we had convinced ourselves that this actually works. But we had to return to the mainland to help on some larger projects there and find more resources to return with. And so after about a year passed, in mid-2024, a small team returned back to Monty's Island, and the Thousand Brains project was officially announced with funding from the Gates Foundation as well as the Korean Electronics Technology Institute. We grew the team from 2 full-time employees to 8 full-time employees. You will hear from all of them today. And additionally, we decided to broadcast the existence of this wonderful island and all the work we're doing here. And so for that, we set up a small harbor village in the south of the island, where ships from the mainland could easily dock in the hopes to build a welcoming community around the project. Next to this small community, we set up a lighthouse to send out messages to the boats nearby. And this way we could publish all of our past year's advances, and interested people could stop by in the harbor village to learn more. We took our private framework code, cleaned it up, and published it under the extremely permissive MIT license, and also put all related patents under a non-assert pledge, so allowing anyone to build on this new approach, commercial or otherwise. And with the announcement of the project, first boats started to arrive on the shores of the southern community. In December 2024, so about this time last year, we hosted our first community event around the lighthouse, and today we hope to continue this tradition. We also published a white paper describing the goals of the project and the principles of the implementation and the algorithm. Additionally, we put together a range of other resources for people who newly arrives on Monty's Island. So a lot of documentation, a YouTube channel where we published almost 150 videos by now, as well as a discourse channel where people can exchange ideas and ask questions on our forum, and our team will answer you guys. On January 1st, the Thousand Brains Project officially started operating as an independent nonprofit, separate from Numenta. And we have a 501c status, meaning that donations to the projects are tax deductible. And if you're interested in contributing to this exciting research that way, you can find more info on our website. As part of our communication efforts, we set up a large watchtower and sent out a team of surveyors to map the settlements on the island so far. Surveying and reporting all the innovations on Monty's Island was a huge effort this year. But we're really happy that ultimately we were able to send an impressive report of Monty's capabilities to the mainland. This preprint was just accepted at Neurocomputation, a really great journal. So you'll be able to see it there soon, or you can check out the preprint, and Niels will cover a lot of the exciting results in there in his talk. We also added more checkpoints along the roads to measure the traffic on them. For instance, we added the ability to measure the amount of floating point operations that Monty uses during learning and inference to compare it to transformers. Later, we also added an observatory on top of the watchtower to make it easier to watch what is happening inside the learning modules and Monty's brain. And Rami will tell you a lot more about these cool interactive visualizations of Monty's brain in his talk. There's a whole repository if you want to test these yourself. All the while, we documented more and more of the project and broadcast new tutorials and explanations in our documentation to the Lighthouse. You can find a variety of information on all the topics around the project here, as well as tutorials you can interactively go through to get started. Over the past years of discussing and testing how to model compositional models, the theory solidified. And so in our recent preprint, we describe the long-range connections in the neocortex and the functions that they could serve. And it contains a lot of detailed descriptions of our theoretical advances over the past years, like the need for reference frames, the role of the thalamus in this process, as well as how the brain could be modeling compositional objects using hierarchical connections. The theory around modeling compositional objects was also turned into actual code and tested. So Monty now has the ability to stack learning modules hierarchically, and we set up new benchmarks and metrics to measure this ability, such as this data set of different logos on different shaped objects. And the team of architects is now working on improving this ability through various adjustments to sensor modules, learning modules, and the policy. Throughout the year, we also improved the usability and accessibility of our implementation. Monty is now versioned and distributed on Anaconda, and we steadily improved our infrastructure around the project. So the roads here, that included fixing bugs and issues, large refactors, introducing rough formatting, switching to different configuration management, and many other improvements. We also mapped out a plan for how we can turn our current code into an easy-to-use platform, and Tristan will talk more about that path to a platform later in his talk. In May, we held a little robot hackathon and built some more peers into the lake of reality. We tested Monty on several real-world tasks, such as a drone, a mobile ultrasound device, and here's a Raspberry Pi with some motors and camera on a Lego setup. And yeah, it was really exciting seeing Monty actually control a motor in the real world for the first time and learn and infer objects this way. If you're interested to build something similar, we also documented all of this in our documentation. We ventured a bit further into the lake with our application of Monty to ultrasound and created a small data set to continue evaluating Monty's performance on this application. So we basically put a bunch of household items into a bag of fluid and let Monty learn these objects through one scan on each of them. And yeah, we'll publish that data set soon if you want to check it out and test it yourself. We set up a little camp below the magical tree of simulation and did several things with the simulator. One is the ongoing work on integrating Majoko as a second simulator, as well as simplifying Monty's simulator protocol and prototyping separating Monty and the simulator code completely. Throughout the year, Learning Module Town has been working on improvements on how Monty can sample and delete hypotheses dynamically, and Rami will give a nice intuition of how Monty's hypotheses evolve over time in his talk. But at a high level, this led to improved noise robustness, speed, as well as the ability to quickly change hypotheses and deal with multi-object environments. So notice when the sensor has moved from one object to another object and quickly update hypotheses. We also improved the connectivity between sensor modules and the motor system to allow for better model-free policies and to coordinate between goals coming from Learning Module Town and goals coming from the sensor module market. We added a little checkpoint before the motor policy city, and that's called the goal state selector in Monty. Together with a new sensor module on the market that can detect saliency, Monty can now move much more efficiently to interesting parts in the world. And that makes both learning and inference more robust and efficient. And this is a feature we're currently extensively testing. We also began constructing another sensor module stand on the market, specialized in the extraction of 2D features like edges in the texture on an object, like here on the Thousand Brains project logo. We also made several theoretical advances particularly on how the brain models object behaviors. We published a write-up of those on our documentation earlier this year and continually refined it throughout the year. We also published and developed a concrete plan of how we could implement this ability in Monty and basically let Monty deal with a dynamic world where objects can move and have behaviors instead of just static objects that never move. We also have been making some progress on figuring out how we could learn causality and use models to affect change in the world, so causal interventions. And as part of that, we also started exploring hierarchical decomposition of goals into sub-goals and more complex action planning. And that tied together some of our theory on hierarchy as well as behavior models and goals. Our theory discussions also led us to explore the concept of attention more, and we got more clarity on how attention could tie into all the other aspects of the theory. In the progress of thinking about all this, we also explored many related topics like fast learning, the role of the hippocampus, categories, and time. And in the past year, we've mapped out many new areas of the island and think we have a much better understanding of the big picture now, even though many open questions still remain towards the east of the island. And if you're curious to how we develop this theory, we spend a lot of our time in Zoom meetings, in deep thought and intense discussions. We meet every week for up to 4 hours. Every once in a while, we meet in person and do this all day on big whiteboards. And every couple of months, we have focused brainstorming weeks where we virtually brainstorm for 4 to 5 hours and think the rest of the day. So a lot of time goes into developing this theory, and over time, kind of the simplest ideas stick, and yeah, key insights evolve. And if you're interested in this process, we also record all of our meetings and upload them on YouTube, so you can kind of be a fly on the wall of how these ideas crystallize. And so as these ideas crystallize, we make action plans of how to implement them in Monty. We prototype them and then integrate them as new features into Monty and publish results. Throughout the year, more boats from interested sailors have been arriving at our little island, and it warms our hearts to see the many exciting ways in which people decide to contribute their time and skills to this project. Will is going to talk more about that in his talk. But big thank you already to anyone who has forked or started our project on GitHub, and especially to those who have contributed to the code. And also, we've had almost 2,000 posts on Discourse, our forum, which have been a pleasure to read and interact with. To make it easier to see different aspects we could use help on, we turned our project roadmap into an interactive future work table that's filterable by different aspects, and Will is going to talk more about that as well. So looking back, it's been a really exciting year. We started the Thousand Brains project as an independent nonprofit entity. We published many of our exciting advances. We're especially excited about the growth of the community with great conversations happening on our forum and amazing contributions coming into our code base. We've made a lot of progress on the theory, all these purple parts. We prototype new ideas and integrate new Monty features, as well as moved Monty closer to a platform that's easy to use. And we tested Monty in several real-world applications. So overall, we're proud of our settlements on Monty's Island and really excited for what awaits us in the next year. And with that, I hand it over to Niels, who will talk about how our approach compares to deep learning and what Monty can do today and its many advantages.
Yeah, thanks very much, Vivian. So morning, everyone. My name's Nils, and I lead the research team at the Thousand Brains Project. And today I'm going to be talking about what Monty's capabilities are today, why we're excited about those, and why that gives us kind of confidence that we're on the right path to developing more general, more capable AI systems. And in particular, this is a question we think a lot about is, how do we actually know that even if we're in an early stage of this path towards more general AI, how do we actually know that we are kind of following the right direction, alluding to kind of that compass that that Vivian was showing before? And to kind of understand the importance of knowing whether you're going in the right direction, I think it's worth taking a page from the story of evolution, as it were, and in particular, the development of eyes. So imagine that you are a simple organism in the ancient oceans of the world, and a predator like this is swimming over you. If you've developed this kind of sheet of light-sensitive cells, that's already a really useful innovation. You can notice that this predator is approaching you and swim away. But there are two ways that you can make this even more useful. One is to form this sheet of cells into a mound, and the other one is to form it into a dimple. And these seem like subtle distinctions, and at this point, they give actually the same effect, which is to give you some sense of what direction the light is coming from. And so when that predator is approaching, you have a better sense of which way should you, run away to. But what's interesting is this kind of subtle decision at the start has profound implications later down the line for what eyes look like over millions of years of evolution. And in particular, the mound leads to a compound eye, what you will be familiar with from insects, whereas the dimple leads to camera-like eyes, as you find in humans and other complex animals with large brains. And neither one of these kind of solutions is the right solution. They both have their own advantages. So, compound eyes are good for a wide field of view. And if you have a small body size, whereas the camera eye is good for high acuity vision, and particularly when powered by these large brains. But what's important is that once you go down one of these tracks, it's very difficult, almost impossible to go back and redesign things from the ground up. Really, you're kind of committed to this initial template in a way that constrains all future solutions you might come across. And we believe that a similar story is playing out in terms of the development of intelligent AI systems. In particular, in the 20th century, it was already realized that neurons were the kind of core computational unit of the brain, and that there are various ways we could mathematically model them. But then in the 80s, it was already apparent that it's very difficult to get these networks of neurons to learn and do anything useful. And so this algorithm backpropagation was invented as a sort of workaround to get the system to learn. And we believe that at this point, there was kind of a fundamental forking between biological intelligence and the AI systems that rely on this backprop, given that it's not a kind of biologically plausible form of learning. This ultimately led to what we are familiar with today, deep learning. But what we are kind of pursuing and what we think is important is this alternative path relying on, first and foremost, local learning, like Vivian mentioned, and also these other key principles like reference frames, distributed modules, things you're going to hear more about today. And we really believe that these are the key principles that enable the sensory motor intelligence we find in nature, and that they are going to be essential to develop a sensory motor intelligence through artificial means. And once again, there's this issue that if you go down this path, once you are relying at kind of the core level of your design on these early assumptions, it's very difficult to remove the issues that come with these underlying assumptions without going all the way back to the start. And we're kind of seeing this play out in the way that some of the kind of key players are attempting to develop improved AI systems today, where kind of the only recourse left is just to scale systems up larger and larger. But as you've likely heard, these approaches are not sustainable from an energy or data perspective. And so I'd like to ask you to kind of imagine by kind of analogy of why this is a problem. Imagine what would happen if evolution tried to develop an eye that has the same acuity, the same kind of high resolution as a human eye, but based on that template of the compound eye. Well, you don't have to imagine it because Kirschfeld in the 70s actually calculated this and provided us with this drawing. But really, this just kind of hammers home the importance of early on really finding what are the key principles that are necessary to reach the end goal that you want. Another way of maybe looking at this is that every technology has its appropriate ideal problem set. So calculators are great for numerical operations, and deep learning is clearly a powerful technology with a wide variety of use cases, what we would kind of summarize as function approximation and generative sampling. So something like AlphaFold is a great example of where deep learning can do really well. But we believe that if you want a system that can interact in open-ended, real-world embodied settings and all the complexity that comes with that, then you really need to embrace a different set of principles, a different set of learning principles in order to develop such systems. And that's what we're really focused on here at the Thousand Brains Project. So that's why we think a lot about that problem. Now then the question is, what gives us some confidence that we are in fact on that right path? And so to answer that, I'm going to show some of the capabilities that Monty has today. But really the kind of high level summary is that we've designed Monty really just looking at neuroscience evidence, and thinking through first principles of how the system should work. And what's really exciting is a whole list of capabilities have kind of just emerged through very little effort in this system. Any one of these capabilities, I should note, would be a kind of significant finding in machine learning. So for example, symmetry recognition. So the ability to realize that as you rotate an object around certain axes, certain objects, then some of these rotations are comparable. That's a very difficult thing to have emerge in a learning system without really baking in that already. But this is something that Monty, we found, just developed naturally. Continual learning, you may have heard about, is a major challenge in deep learning. And again, this is something that Monty essentially has naturally just as a result of how it's designed. But importantly, we didn't set out to kind of solve symmetry or solve continual learning. Rather, we just kind of set out to design a system based on these first principles. And then these are the kinds of capabilities that we're just finding that it has. There's a lot on that list, and unfortunately, I don't have time to talk about all of them today. If you're interested to learn more, we have this paper that Vivian mentioned. We posted it online last summer, and as she said, it's just been accepted in neural computation. So I definitely encourage you to go and take a look if you're interested. But to kind of give you a bit of context before I show some of the results, essentially Monty is looking at a series of objects. There's around 80 objects we evaluated with in a simulated setting. And these are just kind of everyday household objects. And Monty's task is to look at these in turn, learn about them, and then it's going to be presented with an object, and it has to both recognize it and also try to estimate basically the pose of the object, sort of its orientation in space. And so what you see here on the right is, again, just giving you a bit more of a context of kind of what does that look like. But on the left, this wide view is just for our benefit. This is not what Monty sees. This is just to kind of orient you in space and realize, okay, Monty is near a red mug and it's moving over it. But actually what Monty sees, this is something Vivian mentioned briefly and you'll hear more about in Scott's talk. Monty actually just gets this very narrow perceptual input, a bit like looking through a straw. But by combining this with movement, it's able to do all the amazing things that I'm going to talk about soon. And what is the kind of first one of those? Well, the first one is rapid learning. And humans naturally learn very quickly. You'll know that if you look at a new object and kind of study it for a few moments, you can already develop kind of a representation about it. You don't need to study all these images of that object, to the count of millions in order to learn a useful representation. And this is something that we've observed in Monty. So the way we can look at this, for example, is to take those around 80 objects I was describing earlier, show just one view of each object. So it just sees it from a single side, and it just gets to spend kind of a single episode studying it. And then we're going to show a novel view, an entirely kind of unseen rotation of the object. And we're basically going to ask Monty try and recognize it, and again, predict the pose. And just given this one view of each of the objects, Monty can already achieve a classification accuracy of around 50%. And it's worth highlighting that in this data set of around 80 objects and many rotations, chance is just over 1%. So this is a pretty significant finding. The way it does this, I won't go into at this moment, but essentially it comes down to how Monty represents these objects that it's learning based on their actual shape, and also how it's transforming the inputs it's receiving based on its hypotheses. But we can then kind of compare to a deep learning system that gets a comparable amount of data. And in that case, it only gets around 30% accuracy. This is really kind of an extremely challenging problem, as you can imagine, if you've worked with deep learning systems before, to train it given so few views of an object. This finding holds as we extrapolate the data more. So if we give 8 views of the object, you can imagine if you were learning about this one, you would hold it in your hand, rotate it around, look at it from multiple angles. And again, we'll present novel views to Monty. And this time we get around 90% accuracy. So approaching ceiling performance, which is consistent with the idea that you are presenting Monty with the different sides of the object such that it can build a more kind of full representation of it. The other thing we're kind of showing here is if we look at the rotation error, so how well Monty does at predicting the orientation of the object in space, it does really quite well, only about 40 degrees of error, so lower here is better. If we compare again to a deep learning system that gets a comparable amount of data, the accuracy is more around 70%, whereas the kind of rotation error is significantly higher, so around 110 degrees. But it's not just that Monty learns very quickly like humans, it also develops robust representations. And what I mean by that is that we can throw things at the task to make it harder, and Monty can still perform well. If you have some familiarity with machine learning and deep learning, you may think that object recognition is kind of a solved problem. But the reality is that even the best systems today struggle at recognizing objects given unusual and adversarial conditions. So, for example, this pink elephant is very obviously still an elephant to us. But because deep learning systems seem to have an over-reliance on things like color and texture, they can easily be thrown off by this kind of stimulus. So in this case, one of the networks thought that this was a flamingo, presumably because of the color. And so in the case of Monty, we took the objects that it was seeing in simulation and we perturbed them in such a way to make it more challenging, to make it harder for Monty to recognize them. So for one way we did this was to add noise to the location where Monty thinks it is on the object, which it's constantly trying to estimate through movement. We also would rotate the objects in unusual ways that I had never seen before. And then with the kind of last condition, we actually just changed the color outright of the object to something totally different. And importantly, something it had never seen before in the case of that object. And so what you're seeing here is those different conditions along the bottom, where they're becoming increasingly difficult as you go towards the right. And then on the left-hand side, we have, and the kind of blue bars, we have the accuracy of Monty, so how well it's doing at classification. And on the right-hand side, the purple distributions, we have the rotation error. So here we want lower is better. And what's important to highlight is that all of these perturbations that we are doing here are out of distribution. So that means that this is not something that Monty's been trained on before, that it's kind of seen this kind of noise in the past during learning. In the case, for example, of the new color, Monty has never seen this mug in any color other than its natural one. But what's really encouraging is you see this steady performance as we kind of ramp up the difficulty of this task. And just to give a bit of kind of context, again, chance performance in this setting is around 1%. It's also kind of remarkable given that even for humans, for example, in the case of changing the color, the particular data set in question, some of the objects are just inherently ambiguous if you entirely remove that color information. Going back to then kind of the deep learning I was talking about earlier, deep learning systems, this is exactly the kind of perturbation that they struggle on, where it's out of distribution. It's not something they've been trained on before. And it, this is the kind of perturbation that leads to the sort of weird results I was showing of the pink elephant. But it's, so now I've kind of talked about the kind of rapid learning and the robust inference that Monty can do. But we also want the system to be able to act and move intelligently in the world. And one of the encouraging things we found is that with the architecture that we've developed, it's been relatively simple to add in these more intelligent policies. So policies are how a system decides to move in the world, given the learned representations that it develops. And so what I'm showing here is something we call the hypothesis testing policy, where in this particular case, Monty is looking at something like a spoon, or it is looking at a spoon in this case. And it starts here on the handle, and a bit like a finger is basically moving along the surface until it reaches this point. While it's doing that kind of sensing, it's developing some hypotheses about what it may be feeling. And by the point that it reaches this kind of bottom of the handle, its top hypotheses, its top kind of beliefs for what it might be sensing are a spoon and a fork. What it then does is to use the learned models it has for these objects to kind of understand that based on how they would be in the world, based on what it's sensed, where should it move to most quickly distinguish between them? And this is where it then develops this kind of goal of moving to the tip of the spoon, because it understands that that's the point that differs most from the fork that it's familiar with. And so this is exactly what it does. It generates this goal to move to the head of the spoon. This is passed to the motor system, and then the motor system executes that action, and Monty moves there. And what we find then is, as Monty moves to that location, it quickly realizes that the observations it's receiving are consistent with the spoon. The evidence, the belief in the fork representation falls off. And so in kind of larger experiments, this leads to Monty recognizing more quickly and more robustly. A problem I mentioned earlier that is fundamental in deep learning and has been open for many years is this one of continual learning, of being able to add new representations without forgetting about previous ones. Now, naturally, humans are continual learners. We are lifelong learners without any kind of difficulty. And so it can be a bit counterintuitive why continual learning is an issue in the first place. And so to kind of, in the case of deep learning, and so to make this a bit more intuitive, I want you to imagine, how or observe how your brain learns. So if you're looking at an object like this, your eyes move over it, you study it, and if you were the person holding it in person, then you could interact with it physically as well. What you would find then is, very quickly you develop a representation such that 10 seconds, 10 minutes, or tomorrow, I can ask you about this object, and you would be able to recall various details of it without issue. But in the case of deep learning, things unfortunately don't work that way. So in order to learn about this new object, it's not a case of just presenting this new data and then having the system learn. Instead, the new information needs to be interleaved or mixed with these other representations that it has come across in the past. And then it needs to retrain on all of this data. If you don't do this, then what happens is these other representations begin fading. And this is something known as catastrophic forgetting. And what's exciting about Monty is it does not show evidence of this catastrophic forgetting. And in order to kind of demonstrate this, we're again going to use this data set of household objects, but we're going to change the task setting slightly. And in particular, we present an object like the Lego block, and then we ask Monty to try and recognize the Lego block. But then we show another object like the fork, and this time we ask Monty to be able to recognize both the Lego and the fork. We present both of these objects and see how it does. And then we continue this pattern, showing additional objects, but always seeing how the system performs on all objects it's seen so far. And we did this for both Monty as well as a deep learning system that we compare to. So to do well, the system needs to remember the most recent object it's learned, as well as all the previous ones. And what we see here is along the x-axis, we have the number of objects that have been learned so far. And then on the y-axis, you have the accuracy across all of those objects that have been observed up until that point. And with this VIT network, this is the deep learning network, we see exactly this catastrophic forgetting I was talking about before, where as a new task is introduced, the network becomes seemingly hyper-focused on this. All the weights become dedicated to learning about this new task, and it forgets about any information it's learned previously. Whereas with Monty, we have this kind of gradual drop in performance as some of these new objects that are learned are similar to one another, but overall it maintains a really strong accuracy throughout, even all the way up to 77 objects. And it's worth emphasizing again, we didn't build Monty to be good at continual learning. This was just something that emerged naturally. The kind of last then capability I want to talk about is computational efficiency. So you've probably heard how the brain uses a similar amount of energy to a light bulb. And yet you've also probably heard how deep learning systems, the state-of-the-art ones today, need to be trained on massive data centers powered by nuclear plants in order to learn. So the question is, how can we get to systems more like the brain that are much more efficient? And another exciting finding is that Monty is already showing signs of this. So if we look at the compute used for learning, we quantified this by looking at flops. This is essentially the number of computations, the number of mathematical operations that are performed during learning. And I should note this is a logarithmic scale. We then compare Monty to two different deep learning systems. One is a network that's trained on the same data set as Monty, and another one has also been trained beforehand on a very large data set from the internet. And what we find is that even in the case of the network given the much smaller amount of data that Monty sees, we get a significant boost in the amount of computations or reduction in the amount of computations needed by Monty, about 34,000 times less. But if we compare to the pre-trained deep learning system, the difference is even more stark, around 530 million times less compute required. The real kicker, though, is that if we look at the accuracy of these different systems, you see that actually Monty, again, given this small amount of training data, is actually significantly more accurate than the other two systems. Now, the compute numbers I was showing are maybe a bit abstract given their magnitude. So to make this a bit more concrete, if you imagine the amount of compute that Monty needed for learning is the length of a grain of rice, then for the deep neural network trained just on the small task, it would be the length of a shipping container. And for the deep neural network that was also trained on the internet data set, it would be the distance between Manhattan and Los Angeles. So a pretty significant difference. Unfortunately, I don't have time to cover all of the capabilities that Monty has today and that we've explored. Definitely do check out that paper I mentioned earlier if you're interested. But just to kind of reiterate, we're really excited about this because we've seen all of these capabilities emerge really from not that much effort on our part once we had the kind of right design at the beginning. I think another way of looking at this is that this is really kind of fertile ground. And so there are many exciting capabilities that aren't yet on this list. And this is exactly the kind of area that you could contribute if you're interested in working with the Thousand Brains project. With that, I'll hand things over to Scott, one of our researchers, who will be talking about these principles that I've been talking about and how they relate to the neocortex.
Hey, Nils. Thank you. What I'd like to start with here is this question about cortical columns. Like, if you've been following Thousand Brains Project and Numenta before that, you've certainly heard some talk about cortical columns. And because it might not be obvious why they're so fundamental to Thousand Brains theory, I'd like to spend a few minutes talking about what they are, why we care about them, and how they inspire Monty. Cortical columns are found in the neocortex, which is a thin sheet of tissue wrapped around the old brain. The neocortex taps into the more ancient structures below, sometimes augmenting the old brain's sensory systems, and other times granting entirely new capabilities, such as language. Structures in the old brain come hardwired, custom made to serve some narrow but system-critical purpose. Neocortex, on the other hand, it shows up with few concrete skills, but it's eager to learn. A flexible, general-purpose substrate that learns on the fly? It sounds like a good idea, but how do we know it works? Because nature's go-to strategy has been to just keep printing it, and it seems to be working. Even as our brains in our ancestry, in our lineage, they've been getting bigger as a whole, but neocortex does take up a greater and greater portion of it as time goes on. So we know that it does work, but how? One important clue came in the 1950s from legendary neuroscientist Vernon Mountcastle and patron saint of the Thousand Brains Project. While cataloging responses in the somatosensory cortex, he noticed that cells that lay in the same narrow vertical band always responded to the same kind of stimulus. For example, if you were to perform this experiment on me, you might stick an electrode in a region of my brain to respond specifically to sensations of the fingertip, here labeled in blue. While applying various kinds of stimuli to my finger, you might find a narrow vertical region whose cells respond only to light pressure against the skin. But if your electrode crosses into the boundary of into a nearby column, all the cells there might respond only to flexing of the nearby knuckle. Or further again, heavier pressure, like deep tissue pressure. This was a remarkable discovery. And it didn't take long for others to look for the same kinds of themes in other brain areas. So within a few years, David Hubel and Torsten Wiesel famously discovered the same pattern in the primary visual cortex. This was good enough for the Nobel Prize. And their columns identified visual features, such as a specific orientation of an edge. Here I'm showing a handful of orientations here. There in the visual cortex, they also found that columns were bundled into bigger columns, hypercolumns are called, which forms a larger structure that binds together features belonging to the same region of the visual field. Now, columns, or mini columns, as we might say, to distinguish them from hypercolumns in primary visual cortex, they turned out to have real meaning for the brain. And their discovery suggested a new kind of building block for modular design. And this caused a lasting shift in focus towards understanding the form and the function of cortical columns. In the words of Mountcastle himself, columns are the basic functional unit in the neocortex, each performing the same essential computation. But what computation is that exactly? You're probably aware that Thousand Brains Project is rooted in the notion that cortical columns are fundamentally spatial creatures, placing their knowledge of the world into reference frames, which it also uses to guide decision-making behavior in a continuous sensor-motor loop. And while column-to-column interactions are clearly important, enormously important, we begin by taking a more maximalist view of what columns are capable of on their own. And as a motivating example, consider the following situation. Imagine you've been blindfolded and instructed to identify an object placed in front of you using only your fingertip, which is something we do for fun at the Thousand Brains Project. Since your fingertip projects only to some small region of the somatosensory cortex, say a column or so wide, this task rests on the intelligence of just one column. We take our first observation, which feels like maybe a rim of some sort, and then another. So you're starting to think maybe it's a cup or a bowl or something with kind of a rim. And we move over here, we feel some kind of protrusion, and then move back over to the body and feel this sort of cylindrical area. And you start to think, oh, could this be a mug? Okay, yeah, maybe it is a mug. That seems fitting. That seems consistent with all the observations I've taken thus far. Now, think for a moment about what needs to be happening in order for the column to arrive at this conclusion. First, it needs to know where in space its sensations came from. Second, it needed to be able to assemble all these locations into a coherent 3D model. And finally, it needs to compare that model with all the objects in its memory. So let's run through a similar example, now pivoting over to Monty and its architecture and how it's sort of inspired by this example. We'll substitute in Monty's components here. So instead of a finger this time, we'll have a camera, which captures a small field of view image. It's analogous to a small patch of retina, only observing a small portion of the object at a time, like our finger did in the previous example. And then we'll have a sensor module, which performs location and feature extraction on the image batch. You can think of a camera and sensor module, sort of like the retina and the thalamus. We'll also have one learning module, which again stands in for the cortical column. And finally, we'll have a motor system, which drives the camera, controls its movements. At t equals 0, the camera takes in a small part of the object's surface, which it passes directly to the sensor module. The central module determines where the patch is located in space, and it extracts features from the image, such as curvature or color, and it sends this information down to the learning module. There, the learning module compares the observation with points it's seen before, looking for potential matches. At this point, the curvy red patch strongly reminds Monty of locations seen on the mug and the cup, and less so of points on other objects like the blue bowl. Right now, the mug and the cup hypotheses are top contenders, but the learning module doesn't yet have enough data to decide between the two. So where should it look next? The smartest thing to do would be to look for what distinguishes them, in this case, a handle. And so this is exactly what Monty does. And it sends this location down to the motor system. And the motor system's job is to translate the target location into a sequence of commands that will get the camera pointed at the target, such as turn right by 10 degrees and up by 5. Now, after moving the camera, we repeat the process. And the small patch is processed by the sensor module, which again extracts the location and a set of features, and it sends that information back to the learning module. And now the learning module's hypotheses are updated in light of the new information. For each hypothesis, the learning module thinks something like, if I started out looking at this specific point on this specific object, and I then looked over to the right, then I'd expect to see X. If what I'm actually seeing matches that expectation, like it does for the mug, then I'll increase my confidence in that hypothesis. Otherwise, if it doesn't match, like for the cup, then I ought to adjust my confidence in that hypothesis downward. Now, when one hypothesis stands well above the rest, the learning module reports its final verdict. Just quick clarifying point here, which is that the illustration on the left might suggest that there's one hypothesis per object, but in reality, there are many. On the right here, you can see each point there is a different hypothesis, many associated with the mug, many associated with the bowl. And this is what allows Monty to perform accurate pose estimation, in addition to object identities. So to recap, actually, we got one more, which is about learning modules. So very briefly, there are many learning modules that can work, or you can make Monty have many learning modules, just as there are in the many cortical columns in the brain. They can work together, they can communicate with each other to perform faster inference, and they can be communicating laterally, or you can arrange them in a hierarchy to learn and recognize compositional objects. So to recap everything, Brain and Monty share a lot of common features by design. Modularity, modality agnostic functions. So learning modules aren't specifically designed for vision or touch. They've got this narrow input locus, cortical columns and learning modules. Cortical columns and learning modules also have precise spatial mapping capabilities. They function alone or in an ensemble, and also motor output. Didn't get into the biology there of cortical columns, but they contribute to the motor side. So that's how we have these continuous sensor motor loops. And so thank you for your time. I'm going to pass this over to my colleague, OJ, who will talk about how to get started with Monty and run your own experiments.
Okay, so thanks, Scott, for the introduction. So hello, everybody. My name is Hojay. For my part, I'm going to be giving a short presentation on how to run Monty and also how to configure Monty so you can run your own experiments. So I'm going to just jump right into it. First, our code is available at github.com/thousandbrainsproject/tbp.monty. Our documentation is available at thousandbrainsproject.readme.io. After you get the code from the GitHub, I highly recommend you to go to the documentation site. It has additional information on how to set up a conda environment or a programming environment for where you can run Monty. It also has a link to download the YCB dataset. So the YCB dataset consists of household objects that you have seen in previous presentations from Scott and Nils, like the mug, bowl, the bananas, etc. And finally, it also has a link to download some pre-trained Monty models so that you can immediately start playing around with Monty. So highly recommend these two websites to get started. And with that said, I'm going to actually switch over to a different window to actually show you what a Monty run looks like and what you can expect when you actually run an experiment. So I'm going to switch over. All right, so hopefully you are looking at my code editor. Just to orient you a little bit, on the left, what you see here is a YAML-based configuration file that specifies the parameters of an experiment, and I'll explain what that experiment is. On the right is my integrated terminal, and I'll be typing in some commands to run a Monty experiment, the experiment that we specified here. So this is going to be a very quick experiment doing object recognition. So what this is going to do is it's going to evaluate a pre-trained Monty model to identify two objects from the YCB dataset. So specifically, I specified a bowl and a mug. And the goal of Monty is to move around the object, gather features at different locations, and try to come to a conclusion about which object it is sensing. So this pre-trained Monty model has already learned actually up to 77 objects. We're gonna present with two, and the Monty has to try to infer what that is. Okay. One last thing before I actually type in the command on just how to read the configuration file. So the configuration for experiments are basically divided into two parts, one called defaults. So defaults just mean, import these configurations from other files, and they're going to provide the default values, hence the name, defaults, for any kind of parameters that's not specified under config. So if you're familiar with Python, these are kind of like import statements. So it just says import all these configurations from different files. Under config are kind of overrides that you can make to specific parameters that are unique to that experiment. Okay. I know there's a lot of words here, but I'm going to kind of move on to running the experiment itself. So let me activate the conda environment first. tbp.monty. And to run the Monty experiment, the command that you use is python run.py. And you have to specify which experiment you have to run. That's the only required argument. So to do that, you just have to pass it. You just have to specify experiment equals and the name of the experimental file. So in this case, it's just demo. You don't need to specify the file extension and press enter. So what this is going to do, it's going to print out a long list of configs. So this is the full configuration listed out. And soon it should pop up, should start the evaluation. So let's wait a couple of seconds for that to pop up. There we go. Just going to start some, there we go. So you can see here, it's a kind of a crude visualization of Monty kind of moving around, looking at the bowl. It thinks that the most likely hypothesis, MLH, is a bowl with a certain amount of evidence. It's going to move on to the mug. Again, it's gonna kind of move around the mug, explore around different parts. Thinks that the most likely hypothesis is the mug. So yeah, so that was a quick experiment. I know it kind of flew by. If we have time at the end, maybe we can come back to this, but basically the experiment is going to run until Monty detects a match or has timed out. And another thing that I want to note for object recognition experiments or inference experiments, they're going to output, we usually save like some summary statistics of how Monty has performed. So you can find this in the output directory. And what you should see, so this is actually my output directory. What you should see is a folder name with the name of the run name. So just FYI, the run name doesn't need to be the same as the file name. It can be different. It can be the same. That's up to you. And the most important kind of file here is the eval_stats.csv. So if I just double click and open this up, it's a little bit small. So you can see this contains some statistics for each object or each episode that Monty encountered. So in the first episode, it encountered ground truth object bowl. It thought that the most likely object was bowl. We saw that, but there's also many other kind of columns calculating the rotation error, how long did Monty take to get to this conclusion, etc. So this is how we kind of measure performance of Monty, and these are the kind of metrics that you'll see if you go to our benchmark pages. And yeah, so this is what you can expect when you run Monty. I'm going to go back to the slides real quick. All right, so I think previous presentations has alluded to this already, but this is another kind of view of the high level kind of classes that exist in Monty. So Monty itself is composed of one or more sensor modules, one or more learning modules, and a single motor system. It can then be placed in an environment, simulated or real, to run an experiment. So you just saw an experiment for object recognition to identify YCP objects. And every one of these components are designed to be modular, so you can easily swap in or out. So you don't need to just change particular arguments or parameter values, but you can actually write whole new classes for data that you might have that you want to experiment with Monty. As an example of that, this is actually my own configuration for a project that I'm working on. So you'll not see this in documentation yet because I'm not done with the project, but hopefully soon. But you can see that I have, went to Python. I've written up a custom sensor module class. I specify that here in the sensor module class key. I have some custom arguments as well. And you can see that in the config, I'm mostly importing, again, defaults, it's analogous to import from this control experiment. But for this experiment, I'm going to just override the sensor module class. So this is kind of a tip for how to set up experiments if you want to compare kind of two different experiments, like a control and an experimental, without accidentally overriding or changing other kind of irrelevant parameters. So in general, the configuration is written in YAML, so that hopefully you can read through and understand some of the major classes, even if you don't know what Python is. It's supposed to be composable and modular so that you can easily plug in your own sensor module, plug in your own custom classes, such as a sensor module or learning module or environment. Yeah, so that's actually it for my presentation. I know that was a lot of information, so if you didn't get everything, that's okay. Most of everything that I covered is actually written up in running your first experiment tutorial. This is actually one of many tutorials that we have. So I highly recommend you to kind of start with the running your first experiment, go through this. But there's also more advanced tutorials if you want to dig in deeper. If at any point you get stuck or have questions, please feel free to post on Discourse or GitHub issues. Even if you don't have questions, please come say hi. We love meeting new community members and interacting with you all. And for those who are advanced, got everything I said, went through all the tutorials in the past 5 minutes, and actually want to use Monty immediately for your own application, and you need inspiration, I highly recommend you to check out the project showcase page. All right, so with that, I'm going to hand it over to Rami. He's going to show you some really cool interactive visualization tools that exist, and that's going to give you a good sense of how Monty's brains work. All right, thank you.
Perfect. Thank you, Jose. So, yeah, my name is Rami Munir, and I'm one of the researchers here at the Thousand Brains project. Yeah, so today I'm going to be talking to you about the learning modules, and we really think the learning modules are at the core of how Monty learns and infers objects. Scott talked about them a little bit in his presentation. I'm going to go into a lot more details, and then we're going to also show some visualizations that are really going to give you this intuition of what Monty is doing behind the scenes. So yeah, let's start. Okay. So I've just set up an experiment with 3 episodes. Every episode is just a single object at some orientation, and Monty is going to go through the it's just the Monty agent, or like an agent in Monty, is just going to go around the object. Let me run this animation here. So Monty is just going to go around the object, and it's just going to observe or like move its little sensory patch. This is just one learning module working. So it's going to move its own sensor patch around the object. And the goal here is to figure out 3 things. First, the object identity, what that object is it a spam can or a spoon or whatever? and then the orientation at which this object is currently at, and also the sensor location on the object. Because this is a sensory motor experiment, we expect that the learning system should also know where it is on the object, just like if you drop a rat in an unfamiliar environment. When the grid cells re-anchor, it not only knows what the maze is or what the environment is, but also where it is in the environment, because it uses this information to path integrate and do all that fun stuff. So now the cool thing about this experiment is that Monty also doesn't know where the object ends and a new object begins. So if we're at a potted meat can, and then it will just magically switch to a die or a mug, and then it just has to figure out when it did that, or like just basically all the temporal or spatial object boundaries, which is also useful for learning compositional models. So if you're looking at a car and you're fixated on like the car wheel, and then you go over to the car door, for example, and these are like low-level objects, then you want to be able to figure out what the spatial boundaries are and how you like detect when you moved from one object to another. So yeah, so let's open up Monty's brain and take a look inside. And so basically, this is one of the visualizations I'm going to show. I have another one here, which I'm going to be switching between them during the presentation. But we've seen this part before, where the agent is over here. This is this violet or like purple sphere, and we have a step, so we can go through the steps within this episode. The agent is moving, and it's also moving its sensory patch on the object. We could also change the episode to another object and another one. Monty doesn't really know what happens. Like we don't tell it that we change the episode or change the object to another one. One of the other cool things that we could do here is that we can activate like a tracer for the agent and for the sensor patch. So if I run this animation, it'll basically just tell you, these are the parts that we've seen of the object, and yeah, so this is the agent path, and this is the sensory patch path. Okay. Let's now go to talk about the second part of this. So how does Monty figure out what is the next, what is the actual object? So it wants to infer those three things that we talked about before. So Monty comes up with what we call hypothesis space, which is just a collection of hypotheses. And we want to now get an intuitive understanding of what a hypothesis is in Monty. So let me just reveal this other part of the visualization, where I'm going to lay out all of the hypotheses that Monty has about this object. Let's move to like step 6 or something. And now forget about the X and Y axes for a moment. I'm going to discuss them in a little bit. But you could just think of all of these scatter points as just laid out randomly without any patterns. But the idea here is that every one of those little points is a hypothesis of its own. And we're going to investigate further and look into what representation is being captured into those hypotheses. So I can now reveal the third part of the visualization. And so I can select these hypotheses, and it will tell you basically what's in this hypothesis here. So you could look at this right side to figure that out. So for example, if I click on this hypothesis over here, it will tell you I'm seeing the potted meat can, which is the object identity, and I'm seeing it in this rotation or orientation. That's the second piece of information. And then I'm also seeing the place where it thinks the sensor location is right now, which is so the only part of this hypothesis that is correct is the object identity, but it didn't get the orientation correct, or it didn't get the sensor location. So what Monty does at the very early stages of the episode, or like the very early phase, is it will generate some hypotheses. We'll sample them intelligently. I'm not going to get into how it does that right now. but it basically will sample some hypotheses, and then it will start testing those hypotheses. So it will sample some very good hypotheses, for example, some over here. This might not be best hypothesis. Let's see. So it'll basically sample some. So this is a good one, right? So it got the right orientation, it got the right identity, it also got the right sensor location, right? Almost. So some of those are going to, when we test them, they're going to prove that they're good. Others are not. We could also sample hypotheses that are not on the same object, right? So we have many of these views here where we have many hypotheses, right? This is the dice, or the mustard, whatever. So if we go back to just the ones that are on the correct identity, and just to drive this point home about hypotheses, we can also activate here, look at the path that the sensor moved, right? Because the hypothesis is just going to integrate, it's going to get a movement, it's going to transform this movement so that it fits the allocentric reference frame of the object, and then it's just going to path integrate and add this movement to the sensor location. So this is what it looks like. This is the trajectory that it has. It thinks that it moved. We started over here and then we moved all the way here, which really just matches what we moved through with the simulator, right? Start over here and then we just moved this way. So you see that the movements are the same. It's just that it might not be at the same location or the same orientation. So if I look at some of these hypotheses at the bottom here with the low pose error, these all have low pose error, so they all kind of match this one. You'll see that they look the same, but they are just translated, right? It just translated because it thinks that, yeah, the pose is correct, but the location of the sensor is different. But if I move to something that has a high pose error, over here, you'll see that the whole trajectory is just rotated, and that's just, it's trying to fit it into the allocentric reference frame. Yeah, so let's actually run this, let's just replay the animation and see what happens to the hypothesis space as a whole, right? Because we have all of these hypotheses and we want to look at what happens there. So start it again. And so the hypothesis space, it starts, this is the hypothesis space side, so basically it starts with a lot of hypotheses, and then we start pruning them. And the pruning is basically depending on the evidence. So what happens is that as Monty moves, as the agent moves, it will send those movements and features to the reference frame, and that will compare it to what the hypothesis thinks it's seeing, right? Because the movements are also applied in the hypothesis. So it will apply the movement and it will compare it to, it will make a prediction about what it will see, and then it will compare that to what the simulator has sent it, which is the actual observation. And then it will basically build, if it matches, it will add some evidence. And if it doesn't match, it will subtract some evidence. So the evidence added is really proportional to what it sees. So this is what like a typical good hypothesis would look like, right? You have evidence just growing like this. And then we also have the evidence change, which is kind of like the slope averaged over the last few steps. And that's what we use to delete hypotheses or add new hypotheses as a signal of adding or deleting hypotheses. So yeah, so let's just run it to the end. We will see that we have over here just a few hypotheses, I don't know, 10 hypotheses at the end, which is very efficient. What we will look at now is what Monty thinks is, which one of them is the best. So we can just set this to 1. This is the top 1 hypothesis according to the evidence score, the accumulated evidence score, not necessarily the slope, but just the score. And we can try and look at what this one is. So this one's actually a pretty good one. And you can see here that the evidence has been climbing since we started the episode. It's just been adding evidence And it only started, the evidence started only decreasing after we switched to the next object, and then we deleted that hypothesis, which is what we would want. So we could look at this hypothesis, and we can see that it's the right orientation, right object, but also as equally important is the right, it knows where it is on the object. So that's a very important piece of information. But we could also look at what is the second most likely hypothesis, which would be over here. And you can see that it's structurally the same. It's just like a very high pose error, like at 180 degrees rotation, but it's structurally the same, which is that's because Monty focuses more on the shape of the object rather than the texture or the colors. And that's something that we've built into Monty. You could change that if you want, but this is something that is really important to Monty. So we could also look at the third most likely hypothesis, which would be something over here. So that's again, it's the same object, just rotated 180 degrees and 180 degrees. Or yeah, it's keeping the same overall shape. I don't have a lot of time, so I'm going to skip over the die example, but it's getting the correct all the correct information. And then these are just it's the same orientation, but it's different faces over here. It's just swap some of them because again, it's just focusing on this overall shape. But one interesting example over here is the mug, where if I just run this to the end, let's just take a look at what the results would look like. So it thinks that this hypothesis over here, the green hypothesis over here, this is the most likely hypothesis according to evidence. So if we take a look at it, it's an interesting hypothesis. It's the object is in the right orientation, but it looks like it's rotated around one axis, which is the y-axis, and it would be the symmetry, the axis of symmetry, if the handle was not there. So let's take a look at a few more, and you'll see that all of them are actually the same trend, right? It's the same pattern. It's just rotating around that axis of symmetry, assuming that the handle is not there. So what we could conclude that it hasn't really seen the handle yet. And that's what we can also explore by looking at the sensory patch. So we could just remove the cup from here, and we'll see that it moved around the object. It explored also on the bottom of the object, but it hasn't really seen the handle at all, right? So it would make sense that it didn't know where the handle is, and it will just think that all of these are very good hypotheses. They've been accumulating evidence, as you can see here. One other view that we can look at is this view over here. I'm just going to talk briefly about this figure at the bottom, which we're just calling this is also the hypothesis space. If you look at the one with the area under the curve, the highlighted area under the curve, this is the hypothesis space size. So at the beginning, it grows as it thinks that it needs hypotheses, because at the beginning it didn't have any hypotheses, so it needs to sample some, and then it prunes them, right? So it will just prune those hypotheses and then go to almost a few, 10, as I think we've seen in the previous visualization. But then after some time, we'll switch the object with another one, and Monty figures out that it will automatically figure that out based on just looking at the evidence and the slopes and all of that. It'll just figure out that it needs to sample new hypotheses because the ones existing are not really good enough. So we'll trigger what we call a sampling burst. It will just burst some hypotheses over a few steps, and that will increase the number of hypotheses again, and then it will start pruning them. It will happen again when we switch it out with a mug. So you can imagine this also working if you move from one object to another, sharing the same space. So I just want to show you what it will look like here in this different visualization for the cup, because I think it's interesting. Let me just run this again and turn on the hypotheses. So here, what I'm showing here is not the hypothesis orientations. Again, I'm just showing this where every hypothesis thinks its sensor is. So there's a lot of hypotheses. They think they're all over the object. But once we start running the animation, it will just look like we'll be pruning them, but it will also leave only a few hypotheses. So let's do that. And some transparency. So yeah, so we've proven the hypotheses. We are over here right now, and it thinks that there are just a few hypotheses over here. And the hypotheses are all around the object because, again, it hasn't seen the handle. So it just thinks that they're all around. If I turn on the evidence scores, you'll be able to see that it thinks that there are basically good hypotheses all over. So there are very high hypotheses everywhere. Again, it doesn't know, it thinks that this is symmetric. This is what happens when Monty sees a symmetric object or thinks this is a symmetric object. It will just think all of these hypotheses are equally valid or are good hypotheses. And let's just to end this, let's run this again. You'll be able to see that as the sensor moves up and down, these hypotheses will go up and down with it, right? Because we're path integrating. So every movement is just moving those sensor locations. So it will just move up and down with the sensor, which is what we want to see, right? I think I'm going to end it here because I took more time than I should. And just the last thing is if you like these kinds of visualizations, there's a repository for it, tbp.monty, and we have a very small gallery here. And you can contribute to it, or you could just use them to view your experiments that you run. And there are some written tutorials on how to create new ones, and there's also a video tutorial on how to use those. So with that, I'm going to hand it off to Will, who will actually guide you into how to contribute more into various aspects of this project.
All right. Thank you, Rami. That was great. Okay, so hi, I'm Will Warren. I'm the community manager for the Thousand Brains project. I'm primarily responsible for the OSS community. But as you can see from the dotted line, the community is impacting everything we do at the Thousand Brains project. So we're excited to get started with you. So who am I? I'm Brainwaves on the forum. I'm Will Warren on LinkedIn, and I'm wwarren@thousandbrains.org by email. I love it when the community reaches out and has conversations with me, so please don't be shy, feel free. I'm available on all these channels. Okay, so you have taken an interest in Monty's Island, this new form of machine intelligence, and you want to get started. So you buy yourself a boat and you head on over to the open source community harbor, and you look upon the landscape and are overwhelmed by the number of possibilities that you can contribute to. These are all available for the community to have a look at. If something excites you here and you want to work at it, this will be a great opportunity to get involved with the project. So how do you get started? The primary place to go is the thousandbrains.org website. This is a high-level overview of the entire project, the company, the people involved, the insights into the neocortex and the principles that we've derived there, and also links to all the other resources that you have available to you. So it's a good place to start. We also have this contact list, an email distribution list at thousandbrains.org/contact. We send emails out to this list about 5 times a year with important events such as this meetup, but also papers that we've released and so on. You can also contact us on LinkedIn or Twitter or Blue Sky, and that information is on the website. So one of the best ways of getting started and understanding Monty and the Thousand Brains project is our YouTube channel, where we publish all of our videos, our research meetings. They all go up onto YouTube that you can watch. And then we also have this playlist we affectionately call Quick Start, which is about 9 hours of videos. But it's really important and explains all the underpinnings and the paradigm shifts that you have to go through to understand Monty and what the Thousand Brains theory talks about. So this is a great playlist to get started. Kind of the main hub whether we interact with the community is on our forum at thousandbrains.discourse.group. The entire company hangs out here and answers questions and interacts with the community. And so it's a great place to come and ask questions. If you get stuck somewhere, you can ask for help. And if you find interesting research, you can post that on here and we can discuss it. We also post all of our videos back to YouTube as links here. And so we can have discussions around the video content that we're producing as well. Here's an example of a post from Matthew, who was interested in understanding more about how reference frames relate to cortical columns. So please come to the forum and introduce yourself. There's also an introductions channel where you can just say, hi, this is me. We also have the code, as Hojie has shown, on GitHub, 1000 Brains Project /tbp.monty. This is where all of our Python code lives, all the source code for our docs and all the source code for all the tools and visualizations that Rami has showed. That all lives here. And this is kind of primarily where you can make code and documentation changes. We also have a documentation server on 1000brainsproject.readme.io, and this is an exhaustive overview of all the information that we have when we know about Monty and 1000 Brains Project. If you scroll down to the bottom of this main page, there are some great technical resources for getting started with the project in the form of our papers. And there are kind of 7 main sections to the documentation. This is the 6 of them. I'm not going to go through all of these in detail, but I'll just call out a few important pieces. So over in the overview section, there are our benchmark experiments, which show you how Monty is performing against our data sets and experiments. In the how to use Monty section, which is where you'll get started, there's the getting started guide for how to install the software on your machine. And then tutorials for actually running experiments and seeing Monty work in the wild. And just to note that you do not need GPUs to run Monty. It runs natively on CPU-based laptops, so you don't need expensive machines to get this working. And then over in the how Monty works, we have an overview of exactly how all the modules relate to each other within the Monty code base, how learning modules work, how you can connect them into hierarchy, how sensor modules work and the environment, and so on and so forth. And then a section near and dear to me is contributing, how you contribute to the project, how you contribute to documentation, tutorials, pull requests, which Jeremy's going to talk about next, and our request for comments process, which I'm not going to cover here, but is an interesting way if you want to start work on bigger pieces of work in the project. Then we have the community section, which talks about our code of conduct, governance, our license and patent pledge, which Vivian mentioned, and then a project showcase section. So if you've built something in the real world with Monty and you want to create a pull request and show it off in this section of our docs, we would welcome that. And then a neuroscience and theory section where we talk about all the papers that we reference in our work and the papers that we've produced on top of those. There's also the 7th section, which is a very large section called future work. And so this is essentially our roadmap for the next few years of work that we are going to be working on, but you are welcome and excited to see your contributions to here as well. Each one of these subsections has multiple documents underneath it, between 5 and 10 pieces of future work that we're interested in. I'm not going to go through all of those now, but I will reference them in an interactive widget that we built that allows you to find interesting pieces of work, which is located on the project roadmap, which looks like this. So this is the future work widget. It's essentially a table of all of the future work items. And on the left, you can see the title of them. And then you can see the scope of work, the small, medium, and large, the status of them, open, paused, and completed. The metric this improves, compositional generalization, and then the skills that we think you'll need in order to attempt these future work items. And this is interactive, so you can filter by it. You can say, I'm interested in state, and I have a skill of refactoring, so show me all the pieces of work that conform to that. You can see that some are in progress. You can see that Tristan is scoping this one. And so maybe we click on this include state in models, and we go to the detail view of that, and we get an overview of all of the information we have about that piece of future work for you to get started on. So yeah, so if anything here excites you or you're interested in getting started, this is a good place to have a look at. So what areas can you contribute to? As I mentioned, you can contribute to everywhere on this map. A great place to get started is enabling a rough rule. So we have a linting system on our code base. And if you enable one of these rules, you'll get a whole bunch of errors in our code base. And if you go through and fix those, it's a great way to get started understanding the pull request process. And it cleans our code up and makes it better for everyone in the community to use. So we have like a whole bunch of these rules being enabled by Kava and Maymay. So thank you guys for that. You can contribute to the platform and framework for larger pieces of work on the future roadmap. Things like combining the data loader and data set into a single environment interface class, which really moves us towards a nomenclature of a sensory motor system as opposed to the kind of nomenclature of deep learning, which uses data sets and data loader. And so while this looks like a simple refactor, it was actually an enormous amount of work. So thank you, Anna, for doing that and committing it. You can contribute to scaling the system. So Xavier over at ETH Zurich has been looking at process in memory chips. and how we can embed learning modules in those chips and then scale the system at the chip level. And we feel like this may be similar to how GPUs have helped deep learning scale. And so we're interested to see the outputs of these results. So thank you, Xavier. You can contribute to optimization. So here we see Colin, who has worked closely with Tristan to look at backing learning modules with GPUs to see if we can speed them up. Again, you don't need GPUs in order to do this. This was just an optimization. And we also recorded these as videos between Colin and Tristan and published them on YouTube so other people can watch these videos and get involved that way. You can contribute to the simulator. So Agent Rev here has been working on simplifying the simulator protocol and optimizing it. And so this is a number of pull requests that he's made, and this is ongoing work, but it will allow us in the future to switch out the simulator more easily and choose different ones. You can contribute to communication of the project. In this case, Greg Robinson has been producing some fantastic blog posts applying the 1,000 brains theory to kind of interesting human psychology. Artem Kirsanov has created a beautiful YouTube explanation of the 1,000 Brains project and how cortical columns work. And it's really beautiful. It's a great introduction to a sensory motor system. I highly recommend watching that. Matthew has produced beautiful visuals that have improved the flow of the documentation. Agent Rev, again, has created a tutorial for installing Monty on Windows. And we have subsequently rolled that into our official documentation. So thank you, Agent Rev. And here you can see a really small change, just a single line change from Twin Tails, who was fixing a broken link from one of our social media platforms on the documentation. So it doesn't have to be huge. Every little bit helps. You can contribute to real world examples. So here we can see Zachary at Loughborough University is going to be embedding Monty in a robot. And so we're excited to see that work progress over the next little while. Another real world application was enabled when Butterfly Ultrasound gave us a probe on loan. And at our robot hackathon, we built an end-to-end process for Monty recognizing objects at the ultrasound level, which was a new modality we hadn't considered before. You can contribute to sensor modules. So here we can see the Penn State Computer Science department is helping us out by improving feature extraction recognition at the sensor module level. And you can help the community in general. So here we can see a whole bunch of people that have been helping out and asking questions and answering questions of other community members on the forum and posting interesting information on Twitter and our social media platforms as well. And as Vivian mentioned, we are partially funded by the Gates Foundation and the Ketty Institute, but we are now a registered charity. So if you're interested in financially supporting us, you can take that avenue as well. So with that, thank you to all our supporters, all the contributors for getting involved in the work. This is really a community engagement opportunity for all of us, and we're excited to see what work we get done in the future. So we hope you enjoy your mugs. And so with that, I'll end it and say, please join us, go to 1000brains.org or come to our forum and say hello. Also, if you are interested in basing your master's or PhD thesis on Monty, please get in touch. We'd love to have a conversation with you and figure out how we can support you through that process. And with that, I'll hand it over to Jeremy, who's going to talk through the pull request process and how you can make changes to our code base, the docs, and the tools. Take it away, Jeremy. Jeremy, you may be muted.
Thanks, Will. So yeah, I'm Jeremy Shoemaker. I'm a staff software engineer at the 1000 Brains project, and I'm going to explain how you can go through the request process and contribute code and other related things. So an overview of making code contribution. Most of our code changes are made in the tbp.monty repository, so you'll need to fork that on GitHub. You'll need to set it up locally for development, and then you'll need to sign the contributor license agreement, which is pretty typical of open source projects. It lets us kind of, pretty standard thing. You can go read the details of that. Then you make your changes in a branch on your fork and open a pull request, and then the engineering team will triage it and assign it to one of the maintainers to review, and then one or more of the maintainers, and then you'll work with them till they're ready to approve it. And then if the test passes, one of the maintainers will merge the PR. But not working. So all the details on how this process works is in our documentation. You can get more details there than I'm going to cover, but I'm going to cover the broad strokes here. Also, documentation updates are code contributions. So if you think there's a way you can improve the documentation or add something to make it better, please do so. And pretty much every page in their documentation has this nice convenient link where you can click make contribution, and it'll open up a editor in GitHub to let you just make a change there. So quick fixes are really easy to do. So the first main thing you need to do is sign the CLA. This is done in a separate repository. You just basically go there, open up an issue, and do the sign contributor license agreement. You can read it. It's pretty standard. It basically lets us, distribute the changes you've made and gives us permission, to do all that stuff. Making some changes. Depending on what you're doing, different things will require different approaches. But like one of the things I want to point out is that we have a style guide that kind of goes through the different code style things we do. Code formatting is usually done automatically with rough. We have a particular style for how we do our doc strings. Another thing I want to call out here is that we have a code organization guide, which documents how we want to use Python's object-oriented programming features. Some of them we don't want to necessarily use because they make things more complicated than they need to be. And so there's a nice document there that you can go through and figure out how that might fit in. And then we also have a typing guide, which describes how we want to apply type hinting. We don't currently actually run any type checking because our code base doesn't have complete coverage. But as we're making changes, we're trying to add in type hints so that we can eventually get a nice approach and support there for type hinting. So how we triage the pull requests is that the engineering team rotates weekly on who handles triage. And currently that's just me and Tristan. And so it alternates. And at least once a day, we'll go through and look at all the open pull requests that haven't been triaged and then assign them out. And it usually involves checking the title to make sure it matches our conventional commits format, which is in our documentation. You can look there in the code style. Making sure the description adequately explains the change. That way we can kind of, when we reference back to it, we know what was going on and what was the thinking was behind it. We'll cursorily look at the changes to determine who on the team would be best to review the changes, and then assign one or more maintainers based off that to the assignees. One thing to note here is we use the assignees field, not the reviewers field, to determine if PRs has the approvals it needs for a maintainer from the maintainers of the project. So even if you've got multiple reviewers that have approved it, it has to be the assignees that approve the PR. As I mentioned before, we use rough for style checking. I recommend you set this up as an on-save thing in your editor. You can do this in VS Code, and other IDEs have this as well. Running rough check fix -s fix will actually fix a lot of these automatically, and then rough formatting to do just general code formatting to match our style. You could also set these up in a pre-commit hook, but that's kind of less useful in my experience because it's kind of after you've been making the changes and you have to go back and do it again versus just running it when you save stuff. You can run our test suite locally from the top level directory of the repository, but it's just running PyTest and it'll run all the tests. There are various options you could add there, but that'll basically run the full suite. These are also run in GitHub anytime you make a PR. So if they don't pass there, you'll get a notification and have to be fixed before we can merge it. We also have a set of benchmarks experiments that we run to kind of augment our test suite and provide more coverage. These can be run locally, and Jose discussed earlier how you can run an experiment, and you can find the instructions that she mentioned in our documentation. For changes that we think could affect benchmark results, the maintainers will usually run the full suite in our AWS infrastructure to ensure that the results haven't changed unexpectedly. And sometimes that might require further back and forth changes to figure out what happened, what might have caused the differences, if they're expected or unexpected. The documentation goes into details about the benchmarks, talking about what experiments we have, what they are, and then there's a couple of tables of the results that we expect to see currently, and that kind of gets updated whenever we make significant changes that affect the results. Now, the basics of the reviews process is pretty typical. We use squash merges, so don't worry about a messy commit history because it'll all get squashed down. We ask that you please refrain from using git rebase or any other form of history rewriting because it makes it difficult for reviewers to review new changes because GitHub doesn't do a good job of like letting you see the differences. And then just work with the assigned maintainers to get the PR into a state that they'll approve it. And once they do, they'll merge it. Some changes, like I mentioned, will require benchmark runs, and the maintainer will run it and post the results and kind of go from there. Once all the assignees approve it, one of the maintainers will merge it, and then you've successfully made a code change. I want to say thank you to all the people who've contributed and anyone in the future who contributes, because we really appreciate all the work, and it really helps. And any of your contributions usually go into our community shout outs and our monthly review videos, so you get kind of kudos there. And with that, I will hand it over to Tristan to discuss how we plan to evolve Monty into an easy to use platform.
Hi, I'm Tristan, here to talk to you about our path toward an easy to use platform and how you can help us get there. So what is the platform? The platform is the experiment and runtime framework that runs our Thousand Brain system, Monty. Before outlining our current criteria for version 1.0 of the platform, I want to highlight that the current platform version 0 works. Our code is available, and you can use it with enough effort and motivation. Our goal for platform 1.0 is to reduce the currently rather large effort and motivation required for adoption. First, a note on what I think is the main internal challenge to building the platform, the conflicting goals between research and platform development. There are multiple characteristics of research and stable platform that differ. For example, take tolerance for failure. Because of the nature of research, we expect experiments not to work, at least initially, and our tolerance for failure is high. For a platform to be useful, it cannot fail at the same rate as research. So while users may initially be willing to tolerate some failure due to our growing pains, ultimately, the goal is for failure to become surprising and not generally tolerated. Next, how we organize our activity can significantly impact our success in execution. We want to minimize the cost of change in research, as ideas can change rapidly. However, there's only so much change that platform users can absorb. In general, platform users are focused on conducting their own research and or solving their own business problems, and they want to minimize the cost of using our platform in terms of work, time, and money. So we should keep in mind that research is the source of valuable new capabilities, while the platform on which solutions are built must be both usable and stable. Our current strategy for navigating this challenge is to use prototypes and implementation projects as described in our RFC 14. Researchers start with prototypes on their own fork of the main Monty project and should be able to iterate quickly without concern for platform stability and requirements. Once the prototype capability is proven, we will dedicate additional effort to integrate the prototype into the platform. Here's how we define 1.0, our goal for an easy-to-use platform. Ideally, we want to address all improvements that required breaking changes before announcing 1.0. This would communicate stability and garner trust. Additionally, even with all breaking changes out of the way, we want a history of validated use by external parties. I do not think we gain anything by declaring 1.0 only to iterate through major versions rapidly, especially since we already have a version 0 release cadence that communicates our changes may break existing code. Our goal for Platform 1.0 is to reduce the effort and motivation required for adoption. We do this by tracking and eliminating any current undesirable effects we observe. Here are 14 undesirable effects likely to require breaking changes. Platform logging is not sufficiently configurable. Platform internal representations are difficult to visualize. Configuring the platform is complex. Using the platform requires configuration and run boilerplate. Experimental framing is embedded in the platform. Platform is distributed via Conda. The platform supports a single actuator. Main execution loop contains incidental complexity. Reference frames and coordinate transforms are challenging to use. Experiment, platform, and environment are tightly coupled. Hard-coded naming conventions, manual benchmarking, underspecified cortical messaging protocol, which all lead to, as we improve these, will all lead to unstable API. There are also undesirable effects that we're likely to address continuously and gradually. For example, dependency updates and architecture support. Lastly, there are non-breaking changes that we would also like to address, but do not block version 1.0. Insufficient and coupled platform unit and integration tests, benchmarks being used as integration tests, exploiting hardware acceleration, and then integrating kind of standard and legible performance and profiling metrics. And with that, here are 15 items that we want to accomplish before declaring version 1.0. Improved logging, telemetry data emission and collection, improved configuration, reduced boilerplate, distribute via PyPy, multiple actuator support, simplified main execution loop, improved reference frame and transformation experience, decoupled experiment, platform, and environment, remove hard-coded naming, automated benchmarking, cortical messaging protocol v1 published, stable public API, and a modern Python version, and ARM64 architecture support. Now, we have worked out a lot more details behind those items. So with so much to accomplish, we want to ensure that all the work that we do has the desired effect. And for this purpose, we use these tools called, reality trees. The platform current reality tree is a tool where we list all of the known undesirable effects and then figure out what is causing them. The purpose of this reality tree is to stay in the problem space. There are no solutions here, but it should provide you enough context and detail as to why an undesirable effect is occurring. To think through solutions, we have the platform future reality tree, whereas the current reality tree previously listed all undesirable effects. The future reality tree lists all the desired effects. Similarly, for each desired effect, we work out the details of what needs to be done to achieve the desired effect. The things that need to be done, we call injections. These correspond to suggested work that will result in the desired effect. Some of these injections may be as simple as a single pull request, while others can be multi-month efforts. You can learn more about this approach and get into all the details starting on this course. Additionally, as mentioned earlier, the project roadmap will eventually include all injections, making them easier to find, especially on the future task widget. And that is our initial plan. However, that's only our plan today. You probably have good ideas for improvement of what problems to solve that are not listed in our reality trees. And ultimately, it will be your contributions that will propel this platform forward. Also, we are hiring. Join us. And with that, up next, Jeff will wrap up today's presentations with a big picture view of what we are working on and our vision for the project.
Jeff, please remember to unmute yourself. Thank you.
Maybe if you stop sharing again, it will be easier to see the unmute.
That was the key. Thank you. It wasn't available when I was sharing. Nowhere to be found. Sorry about that. A little bit more practice would have helped there. Hopefully, we can see that slide. And I have a very short presentation. And I'm going to talk about two things. I'm just going to talk about our mission again. I know Vivian talked about this a bit. I want to give you my take on that. And then I want to give you sort of a really high-level picture of the goals. You've heard a lot of details in these presentations, a lot of amazing work that's been going on to the system, but sometimes it's really helpful just to bop up again and take a look at the top picture. So let's just start with the Thousand Brains Project's mission. It all starts here. Vivian mentioned this. It can be summed up in this one sentence. We're creating machine intelligence technology based on neocortical principles. There's a lot in this sentence. I want to unpack it. First of all, I prefer the word machine intelligence over artificial intelligence. To me, today's AI is not really intelligent. It doesn't mean it's not useful. It doesn't mean it's not great. It's just not the real thing. And we're trying to create the real thing here, the things that we all can agree to, just since we're building machines that work the same way that biological intelligence works. We're really focused on building a technology. We're not focused on applications. We're not trying to build a business. It reminds me, I don't want to get too heady here, but I really do think what we're doing is sort of what happened in the 1940s when the pioneers of computing set down the technology framework for computing, which lasted for many decades and still today. And I think that's what we're doing, something similar here. We're building the fundamental technology and the theory behind what intelligent systems are like. And of course, we're using neocortical principles to do this. And we're only able to do that because we've spent so many decades working on this and made amazing progress in understanding how the brain works. So that's our goal. That's our mission. I thought I mentioned just again, remind you of the top principles involved here. The top principles, my top three, we can disagree about these. My top three principles is that these systems are sensory motor. They have sensors which sense the world. We're not feeding some abstract data into them. The sensors that sense the world, they're moved through the world, so there's motion involved. Sensory motor integration is used for learning, for inference, and for solving problems. So it's not an add-on piece, you add a motor to it. Every learning module has a motor output. The whole system is sensory motor. One of the things that's people just, I don't think, appreciate enough. When you learn this way, you have these structured models. You heard about reference frames. Everything that's ever processed in the brain and in Monty is not only what it is, but where it is, where being the pose, location, and orientation. That's how knowledge is structured in your brain. That's how knowledge is structured in Monty. This provides all these amazing abilities to manipulate knowledge, to rotate it, things, to navigate through a reference frame or through a structured space to solve problems. This is really the key to the strength of the system. And of course, it's a highly distributed architecture. The learning module is a very powerful thing. But really, the systems become powerful because they can apply them. The same learning modules can be applied to different types of modalities, different parts of hierarchy, allows us to build systems with different sensory modalities, different embodiments, different levels of capabilities. It's an incredibly modular system that nature has discovered, and we're trying to replicate. You've heard about some of the attributes that's come along with this. Continuous learning, can't overemphasize how important that is. To make a system that actually solves real world problems, it has to, at moment to moment, learn what the current reality is. Where did I leave this thing? Where's my tools? What's happening? Who's there? What things have just changed in the last minute? And the system has to be able to do those things. And of course, along comes with that is a super low power and minimal training. Our goals for 2026. We have three broad goals, and you've heard about all of them today. And this is our goals for 2025. These are our goals for 2026. This is a system. First, we have to expand our community. We're 8 people full-time, which is very small. What we're building is going to be much, much larger than any one company or organization can manage. We need to get more people involved and excited. We'll give you a good introduction of how you can get involved. If nothing else, tell people about the Thousand Brains Project. We think this is really important. Then you heard from Tristan about how we have to build a platform. That's really essential too. I spend most of my time, and some of the research people do, about adding capabilities. I used to say research, but I changed it today to say add capabilities because actually it turns out the number of things we have to do research on is decreasing. there aren't too many big things left to figure out. And we're moving more into a sort of an implementation and mode on these things. So as you've heard throughout this, we did do a lot of work on compositional models, how world objects are structured of other objects. We understand that, we're implementing that. That should be integrated completely into Monty this year. We learned last year how the same learning modules can learn the behavioral dynamics of the world, how things in the world change. And of course, the world isn't static. But fortunately, we didn't have to come up with new algorithms for that. It's an amazingly simple switch from what the inputs to the learning modules are. Now we have models of behaviors, how things are expected to behave over time. And once you have those two things, once you understand the structure, the static structure of the world and then the dynamic structure of the world, we are able to now start approaching goal-oriented behaviors, like how do we use behaviors to manipulate the world to reach various states. This is all coming together. I don't expect that we'll have all this implemented this year. I know we won't, almost certainly, but I think by the end of this year, our goal would be to have a very solid theory of goal-oriented behaviors and understand causality, so that perhaps in 2027 we'll have really fill out the whole thing. I want to emphasize again how that there's really not a lot of major things left to done. The beginning of this project moved very slowly for years and years. It was difficult to make progress, but now things are moving quickly because we have all these pieces in place, and it's now just sort of rejiggering the components and adding some new things to it. So it's getting to be a very exciting time for this whole endeavor. And with that, I want to thank for those who are listening today live, those who are listening online later, those who have contributed to the project so far. We talk about you all the time. We really appreciate the effort you do. And I think now I'm going to leave it, and we're going to now do some Q&A. I think Will's going to moderate that if I remember correctly.
That's right.
I'm
Thank
going
you,
to
Jeff.
stop sharing.
All right, let's get into it. I'm going to sort these by upvotes. So if you're interested in upvoting a question, you still have time. You can go do that. So first question, do you expect that this sensory motor approach can also be useful for cognitive functions? Who would like to take that?
Any one of us can answer that one. Okay. I'll start, sure. We know that studying the brain, that the neocortex does all these different things. It does and all the cognitive functions we think about. And yet it has the exact same architecture, are very, very similar everywhere. And so that's the starting assumption. The evidence is strongly suggestive of that all cognitive functions are built on the same principles. And only very recently did we start really getting to deeply understand that. We haven't discussed it publicly anywhere yet. We knew that if we just started focusing on how learning modules work in a generic sense, like how can I sense through vision, how can I sense through touch, how can I sense through hearing, and understand the world, that the principles we learned there would apply to higher level cognitive thought, and we're now beginning to understand that. So the answer is yes, but we haven't really explained it yet completely. If someone else wants to jump in, they can do that too.
Thank you, Jeff. Okay, next question. Is Monty capable of moving through time in time series data? All right, Vivian, do you want to take that one?
Yeah, I'm just raising my hand now. I guess we can all just raise hands if we feel like we have an answer. But yeah, so fundamentally, Monty is always moving through time in the sense that it senses different locations in space over time. But you're probably referring to like basic time series data, where the progression in time is not kind of anything under Monty's control. And so that's going to be one of the things that we're going to work on a lot next year, which is what Jeff alluded to, modeling object behaviors. So how things change over time and learning models of how things change over time. So at the moment, Monty's models don't have a representation of time, but we're planning to prototype and integrate that in the next year.
Great, thank you. Okay, next question. Can inference and training run at the same time, as I suspect our brain does? If so, is there a moment where it decides when does it need to create a new model for a new object? Okay, Vivian.
All right, well, I'll answer that because I worked a lot on that part. So yeah, inherently there isn't really, like you said, in the brain, there isn't really a distinction between learning and inference. We are always learning new things and we're always doing inference all the time. And we actually need to do inference to be able to recognize that there's something new that we need to be learning. And so Monty can work the same way. We currently, in our configs, you'll see kind of setups for training and evaluation. But the only difference between the two is whether the model, the things that Monty observes during its exploration will get stored permanently in memory or not. Everything else is exactly identical. And so if you do learning, Monty will first start doing inference and will start to recognize whatever it is sensing. And if what it is sensing is not matching any of its models, it will create a new model and store all the points it just sensed in that new model. If it recognizes a model, it will just integrate the past observations into that model and kind of fill in the gaps that exist in that model, make it a bit more filled in, add more details to it. So yeah, if you run Monty in kind of training mode, it will do learning and inference.
Great.
Yeah, and maybe just to add to that, Vivian mentioned that we've had some more ideas on attention recently, and most of these haven't been implemented yet. But in general, our view is going towards that attention is essential for a lot of things, including, learning. In general, you don't, certainly at a cortical level, learn much about the world unless you're attending to something. But I just thought I'd mention this because I think in your question you asked about teachers and the importance of that. So although clearly you can learn without a teacher, and just by exploring the world, in humans, this kind of shared attention between either parents and children or teachers and children, where you kind of both look at something and then the teacher describes what's being seen. That's really essential to how learning takes place in humans, and you can imagine something similar working in Monty. But that would be kind of bootstrapping and just kind of making the process go quicker. Like Vivian says, you can totally kind of move flexibly back and forth between inference and learning.
All right, great. Thank you, Niels. Okay, Agent Rev asks, so far your focus has been mostly centered around vision, along with a lot of discussions about touch too. In the documentation and some of your videos, you talked about eventually dealing with abstract concepts, language, world models, logical reasoning, and more. I suspect this might require more types of sensor and learning modules for the other brain regions, e.g. motion, audio, scene mapping, attention, reasoning, prediction, etc. Along with a distributed associative database of sensory SDRs on live global workspace to solve the binding problem, all of it optimized to run a standard workspace. I'm curious to find out how far the theory of columns can be pushed. All right, Jeff has raised his hand.
It's a tough question. It just relates earlier about the question about, can the column theory apply to cognitive things? And we just recently in the last few months sort of had some further insights in this, which I alluded to. So I don't want to get into too much detail about it because it's very, very speculative. But we accept the fact that all columns are reference frame based and all columns have a reference frame. The question is, what does a reference frame refer to? And the way we currently understand it, they're very much tied to physical things in the world. Like you even when you learn like mathematics, you do it by looking at images of equations and things. So when you learn about history, you look at pictures of images of the world, or and so on. But is an answer here that might go beyond what most people would be able to capture right now, is that as you go up the cortex and you go higher and higher, what you end up with the representations of objects that are very compositional. They're very objects composed of objects composed of objects. And the power of abstract thinking comes from that, not from the reference frame itself. And so you might even use very simple reference frames and movements to learn mathematics and language. But the features that are being fed into those reference names are themselves are much more abstract. So the abstraction comes less from the reference frame, but from the accumulated compositional objects that are being represented in reference frames. I hope that was maybe slightly helpful. I don't know if it was.
All right, thank you.
Yeah, I think maybe just emphasizing that, yeah, we don't think we need to build custom learning modules for reasoning or attention or language or something like that. They will all get fundamental sensory input at the lowest level, and then if you go to higher up in the hierarchy, they get the more kind of compositional features, like the outputs of other learning modules that have learned entire models. And so kind of some of the things you mentioned in the question was like reasoning and prediction. So those things would be things that are going on inside each of the learning modules themselves, and not specialized to one specific region. All of the learning modules are doing prediction, basically.
Great, thank you. Okay, I'm going to go over to one of the already answered questions, but it was important. So what's the largest scale Monty has been trained on in terms of data and compute? Do we have confidence it will scale well in performance? And if so, why?
Yes, so I'm happy to take this one. So yeah, this is a great question, and someone else asked something similar. So in terms of the experiments, for example, that we do in the paper, and just generally, 77 objects at 32 rotations is about the most that we've looked at. And not because we couldn't look at more, but really, as you've probably guessed from the results we were showing, we're really focused on showing what Monty can do and exploring what Monty can do, given very small amounts of data, like what humans can learn from. But in terms of kind of scaling, there's more details in the paper if you're interested. But at learning, if you remember those charts, we could learn on 10,000 objects, and it would still use, because it scales linearly, you could learn Monty on 10,000 objects, and it would still use fewer flops than that very actually short deep learning run, the one that had the same amount of training data and is just learning 77 objects. So the difference there is huge, and we're not concerned. At inference, it's a bit more subtle because, again, in the current version of Monty, the amount of flops, again, scales linearly. But really, the current implementation of Monty is very naive. We've not, as I mentioned earlier, we've not designed it to be computationally efficient as a kind of aim or a goal, aside from some very basic optimizations. And so there's a huge amount that could be done to kind of make that nonlinear. Everything from sparsity to hierarchy to reuse of models, all these things that we believe the brain's doing, and that we eventually want to implement in Monty. So yeah, both at learning and inference, I think yeah, the amount of flops is definitely not our kind of current concern. It's something that should just kind of come naturally from the design of the system.
I'd like to ask a question, which I'm not sure if the person who posed the question was thinking of this, but that's how we've talked about scaling to kind of the task. But another way of scaling is how many learning modules have we used at once and sensory motor integration. Because, in the brain, we have 150,000 of these, and yet we can do a hell of a lot with one learning module. And so we spend a lot of time just exploring the capabilities. But another question is, what's our confidence level that we can scale up the number of learning modules to, and I don't know, I actually don't know the answer to that question, so someone else can answer that.
Yeah,
Yeah,
maybe just to
so I
say that
guess
it's. Go ahead, Vivian.
Yeah, on a concrete level, we haven't really scaled it beyond like 16 learning modules, but it's mostly because we haven't done a lot of hierarchy yet, and at some point you can't just add more sensors to a system and still get meaningful input on different parts of the object. But so once we add hierarchy, we're going to run more experiments with more learning modules. And since Monty is an inherently very parallelizable system, like one thing you can do is you can just use a bunch of CPUs and parallelize all the learning modules across them, or other custom hardware that, like Xavier, for example, one of the university collaborations is exploring on other types of hardware to scale it to actual thousands of learning modules.
Great, thank you. Okay, next question. Ray asks, do you use spiking neural networks in Monty? If not, do you think that the spiking behavior of biological neurons is relevant to an artificial intelligence in any way?
Yeah, I'm happy to at least start on this one. So yeah, this is another interesting question. For anyone who's been, I guess, following work associated with Jeff for the last couple of decades, first Numenta and then now TBP, you'll know that there's been kind of various levels of biological realism and in the kind of systems that are being built. And so this is kind of a struggle we're constantly thinking about and trying to figure out, what is the right level of abstraction? And that includes whether you need to model things like spiking neurons. In general, our approach is to try and kind of find the most abstract level possible that still captures the kind of key computation we want. So, for example, with HTM and the neurons that were used in HTM, they found this kind of interesting balance between the old kind of point neurons and a kind of overly complex multi-compartmental neuron, if that means anything to you, like trying to get the key role of dendritic branches and what those were doing of putting a neuron into a predictive state. And that's actually something that's still made its way into Monty today, even though we don't have neurons in the same way. We're still capturing this notion of kind of prediction following movement and things like that. So then the question is, what might be the kind of key things that spiking is delivering? And every now and then in our research meetings, we talk about things like, temporal codes and how, maybe spikes at certain times relative to a background phase might be important and things like that. But a lot of that is more about how the brain is doing it and doesn't necessarily need to constrain how we implemented Monty. So I guess the answer is that at the moment, we don't have anything where we think we definitely need it. And given the complexity of training spiking neural networks, it's something we want to avoid if we can. But it's also not something that we've ruled out that there might be kind of elements, at least, of what spiking neurons are doing. Things like STDP, causal learning, some of these kind of key elements that we might take out and integrate into Monty.
That was a nice explanation, Niels. I think, something like SCDP, which is a spike timing dependent plasticity, is maybe critical, but you can achieve that without spikes. It's just really a temporal causality that you're capturing. And so we've only put into the theory things we absolutely think have to be there to support all the principles. But Vivian often points out that you can build learning modules any way you want, as long as you adhere to the cortical messaging protocol. So if someone wants to come along and say, I'm going to build a learning module built on spiking neurons, well, you can do that, and maybe you'll do something amazing. But I think it would be more amazing in terms of performance, the power reduction, something like that, as opposed to like some great new capabilities. I don't think that's going to happen, but it might be a great way of building stuff if you have the right semiconductor substrate and you know how to build that, and you might get tremendous efficiencies or something like that. So it's not like we rule it out, but I don't think from a principles point of view, it's essential.
All right, great. Thank you so much. Avinash asks, how soon is Monty expected to be capable of language learning?
Yeah, I think we have several posts around that on Discourse where we go into more depth of what we think of how language could be modeled in Monty. I think maybe one important point to make is that we don't think language is where a system should start. It's not like you start out learning language. A baby comes into the world and it starts out interacting with the world and learning a bunch of different things, but language is kind of one of the last things that come on top of everything else of learning how to move and walk and interact with toys and all that. And so once language comes into Monty, well, following kind of this basic principle that also columns that learn models of words, for instance, have the same basic structure, the idea is that it will kind of fall out naturally from the other things. It's just based on what kind of environment you place a Monty system. If you place Monty in an environment where it hears language or it reads words, it will learn models of these letters and words and sentences, and it will be able to associate meaning with words and kind of ground those words in physical reality. But yeah, since we haven't really scaled Monty and made it like hierarchically deep in the way that would be necessary to get kind of multimodal integration and language associations with meaning, we haven't really had a way to test this.
Just adding on to that a little bit, if you think about language, what it mostly is a way of transferring a model I have in my head into your head. And so often we express language in terms of the same sort of communication protocols we have in Monty. Like, oh, imagine this: you're at this intersection, and when you know there's that store over there, well, inside of there you'll find the such and such, and yesterday we did this, and you basically recreating models in one person's head into another person's head. And once you realize that, it becomes not very mystical at all. But it does require you have these existing models. So as Vivian just said, you don't start with language, you start with models of the world. And then once you have models of the world, we can talk about how to communicate them to someone else. And I actually think the process is going to turn out to be fairly simple.
All right. All right, next question. We have time for a couple more, and then we'll call it. But Falco asks, is the hypothesis generating and pruning based on neuroscience? Rami, do you want to take that one?
I think I'll try and take a stab at this one. We've already worked out a lot of details about how a single hypothesis in a column, like a hypothesis about orientation, can actually transform the movement that is being sent from the thalamus. So we think there are hypotheses about these orientations in the column, but the question here is how many can exist simultaneously in a column? That's a bit more complicated question. We've discussed this a lot in our research meetings about how maybe we can have different populations of these representations exist, and we can oscillate between them based on phase or oscillations or something like that. And we could also imagine maybe like a fixed point attractor network where these can compete together. But it's something that again goes back to the abstraction of like how biologically plausible should this be and what do we need in our system. So yeah, we think there are multiple hypotheses. Whether they can all fire together at the same time or we oscillate between them, that's a kind of a different question.
I agree with everything Rami just said. I'll just add, in the neuroscience, we have a pretty strong hypothesis about one form of keeping these hypotheses going, which is a union of sparse representations. So you can literally activate multiple hypotheses in the same set of cells at the same time, and nobody gets confused. We've shown that how that works mathematically, and there's a lot of biological evidence for it. We don't do it that way in Monty. We could, but it doesn't, we don't have to model it that way. We can do it other ways and work just as well. So the answer is, yeah, it's going on in the neuroscience. It's going on in the biology. We think we know some of the ways it's happening in the biology, but we're not actually emulating those. We're just achieving the same result in Monty.
And yeah, maybe just to add as well, this point about generating. So Rami was showing some results earlier from some nice work he's done recently where in kind of the latest version, not necessarily the version if you just kind of use Monty and most of the configs, but the latest version will expand its hypothesis space dynamically. And that has a lot of similarity to how we think kind of sparsity is kind of playing out in the brain, where basically when there's a prediction error, when something is unexpected, suddenly lots of neurons are active. And that's something that Monty kind of does in this version that Rami's been working on, where if the system's failing to understand what it's seen, suddenly it kind of bursts this hypothesis space and expands it. So it's, yeah, I guess just another example of something that has a flavor of the neuroscience without necessarily needing to be implemented, to the letter in the same way that the brain would.
All right, great. Thank you. Okay, so two more questions. So Robin asks, how is the sensor module able to infer curvature? Is it analyzing the 2D pixel data, or does it get depth input from the sensor?
Yeah, I can do that. It's pretty quick. It does get depth input. So yeah, we use depth input to both determine where the sensor is in space. Because, for example, if you have a camera, the patch itself on the object is not where the camera is. So we need to know the distance to the object. And then plus if from the patch and the depth values within that patch, we can calculate the curvature and the surface normal.
Maybe it's worth just adding though that yeah, right now we're kind of limited if we want to apply Monty in the real world to having some sort of depth camera like time of flight and things like that. But one of the items on that future work section that everyone was alluding to is to use things like parallax, both motion and binocular, to extract depth because this is more similar to how the brain does it. So if that's something you have familiarity with and would be interested in working on, that would be yeah, that would be really cool.
Yeah, and I guess, yeah, it also depends on what modality you get. So for example, for the ultrasound project we did, it wasn't like a depth camera itself, it was the ultrasound image, which includes information about how far the probe penetrates into the whatever is scanning. So basically you can write custom sensor modules however you like and connect them to whatever particular sensor you have. And the sensor modules can extract whatever features you want them to extract. And they can extract them however you want them to be extracted. The important thing is that sensor modules need to be able to extract where in space they are and what orientation they're sensing there. And that's part of the cortical messaging protocol so that the learning module can then infer how it has moved from the previous step.
Great, thank you. Okay, last question. It's a good one. It's a big one. Do you believe that Monty would be able to achieve knowledge generalization and creativity without modeling hippocampus and neuromodulators as reward signals? Nobody
All
wants
right, I'll take that one. No problem at all. Can you just repeat the question again? I want to make sure I get it all.
Yeah. 1 second. Do you believe that Monty would be able to achieve knowledge generalization and creativity without modeling hippocampus and neuromodulators as reward signals?
Okay, so there's a bunch of things in there. First of all, we believe we have to model the hippocampus. And one of the ways you have to, not just for this creativity issue, but we have to model the concept of attention and fast learning that occurs in the hippocampus. So we've been talking a lot about that lately. The good news is that a lot of people believe that the neocortex is a derived structure from the hippocampus. So there's analogous processes to cortical columns in the hippocampus. So we don't have to introduce new fundamental features. We just have to introduce new concepts of fast learning and slow learning and temporary learning, which all fits within the current framework. The neuromodulator one is interesting. There has to be something that tells the system to learn or not learn. All right. And it could be simple as a switch that says we want to learn, learn everything. Or you might say, oh, well, we want to have value-based learning, like learning only things that have certain types of values. I think when we think about neuromodulators, that's really what they're about. They're mostly about deciding when to learn. They can also be, they get involved when we're trying to do like understanding causal relationships in the world. Like, oh, these things led up to this desirable events, like reinforcement learning. So we're going to model some of that, but I think the idea that you can generalize knowledge and do some, they don't really require that. We're going to have those in the system, but the system basically learns models and can generalize some knowledge from those models, but we will have to have at least some sort of equivalent to neuromodulators decide on an application by application basis, what do we want this system to care about? How much do we want it to learn? Do we want it to be fixed? Do we want it to learn all the time? Should it learn everything or just certain things? Those are kind of application specific problems. They're less about theory, overall theory. So a little bit of a complicated answer to your question, but it's a great question. And we think about these things a lot.
All right, great. That was our last question, everyone. So I just want to say a big thank you to all the panelists and all the people that spoke and the presentations, and for all of you for joining and getting up to speed with everything that's been going on in Monty in the last year. Final call, come and join us. Come join this journey where we rebuild a new type of machine intelligence that we believe is the future of machine intelligence. So thank you all and have a good day.
Yeah, bye.